All right, here I have a long chain alkane. All right, there's pretty much nothing special about this molecule, okay, other than its length. There's nothing really that makes any part of this molecule any different than any other part. Over here, these carbon atoms aren't going to react any differently than these ones or any other atoms in the molecule. Okay, but in organic chemistry, quite often we have different characteristics in a molecule. For example, say I had a double bond here. Okay, now this double bond is going to have chemical properties that are different than the rest of the molecule. Okay, so by putting that double bond there, I have added functionality, chemical functionality to this molecule. Right. So what that means is this double bond is now going to react chemically in a different way than this plain old alkane part of the molecule will react. Okay, so that additional functionality is why we call this a functional group. Okay, this is a fairly simple functional group. Many functional groups have other atoms. In fact, most functional groups have other atoms involved that are not carbon, they're not hydrogen. Quite often, oxygen is involved. So say I have an OH. All right. Here is a different type of functional group. I'm adding a different functionality to this part of the molecule. All right. And depending on the nature of what is attached to my carbon chain, or what kind of bonding I have between the carbons, for example, and depending on what I have there, it will behave chemically in a different way, and the molecule will have different characteristic properties. All right. And we need to be able to recognize some of these basic functional groups and associate them with their names. Okay, so the OH functional group, when I have that oxygen bonded to the carbon chain, this is what we call the hydroxyl group. Okay, so just like in inorganic chemistry, the OH negative ion is the hydroxide ion. Well, in organic chemistry, when the OH is attached to the carbon, we call this a hydroxyl group. Okay. So similar name. Often we see this YL ending to group names. Hydroxyl. If I have something just a simple carbon constituent, okay, like a single carbon side group, this would be, so it's one carbon that I have attached, so that is a methyl. Okay, that YL again, very common in the naming of groups that are attached. Okay, so this hydroxyl group, a molecule that has that hydroxyl group in it, we call an alcohol. Okay, so for a simple example, let's look at ethanol. Right, here is ethanol. We have two carbons, and then attached to that OH. Okay, so this is ethanol. It is an alcohol. Okay. So the hydroxyl group is our functional group, and then that makes it an alcohol. All right. So just remember, OH is the hydroxyl group, and compounds with that hydroxyl group are alcohols. And alcohols, now we're most familiar with ethanol. That is the alcohol that many people like to drink. But there are other uses for alcohols. They are good solvents. They're often used in cleaning products. You have probably heard of rubbing alcohol. Well, rubbing alcohol has 3 carbons arranged like this. It's isopropyl alcohol. There's the propyl part, and then a common name for that, iso, indicating the middle carbon is the one with the alcohol group on it, or the hydroxyl group attached. All right. So isopropyl alcohol or ethyl alcohol. These are common names, by the way. The standard naming we will talk about in another section. But its standard name would be ethanol or 2-propanol. Okay, but these are different alcohols. Another alcohol would be methanol, which would just look something like this, or quite often we would just write that out as CH3OH, because it's not much of an abbreviation really, even to put that line there. But this is methanol, and methanol is actually very different from ethanol in that methanol is very poisonous. So if you have some ethanol that is methylated with the methyl alcohol, then it makes it poisonous. And that combination is often used for paint thinner, cleaning of different things. It's used in solvents, a variety of applications. Another thing that alcohols are good for is they're flammable, so they make fuels. They burn very cleanly, and that's why there's a big push these days to use ethanol as an alternative fuel, because it burns cleaner than the octane type fuels that we are accustomed to using. Okay, so let's look at some other functional groups. One functional group that is similar to the alcohol is an ether. Okay, an ether is a molecule that it has a side, it has its carbon chain, and but instead of an OH like the alcohol, it has a second carbon chain. Okay, it can be any different type of carbon chain, but this type of molecule is an ether. All right, the most common ether is diethyl ether, where we have an ethyl group. Remember, the YL ending is typical of group names. So ethyl and then diethyl ether is the name for this compound here. And it was formerly used as an anesthetic because it would put people out. But it isn't used for that purpose anymore due to the side effects of nausea and other such effects. Right? But ethers are also commonly used as solvents. They will dissolve many different organic compounds, and they also are easy to remove because they have a low boiling point. Right? So, but the key thing here to recognize, associate the name with this group where the oxygen atom is between two carbon chains of any length. Okay, it's just they're connected to two carbon chains. All right, so that's the ether, and similar in nature to the alcohol, except that instead of a hydrogen, I have another carbon chain. All right, so let's look at an aldehyde. Right, this is another functional group, and this functional group is it can only occur at the end of a carbon chain. Okay, this is what the aldehyde functional group looks like. You have your carbon chain, and at the end of that chain you have a carbon that has a double bond to oxygen, and then on that carbon you can tell me how many hydrogen atoms would be attached here. I have 1, 2, 3 bonds shown for that carbon, which indicates that there is one hydrogen there that I'm not really, I don't normally show that, okay? But that hydrogen is a part of the aldehyde, and for that reason, there's only one place where I can connect a carbon chain, because that H has to be a hydrogen for an aldehyde, right? So that only leaves me with the one place to connect it, and so aldehydes are always at the end of a carbon chain, okay? And the simplest aldehyde actually is, if you just have that one carbon, that would be kind of a double aldehyde, if you will, having a hydrogen on either side. This is formaldehyde, often used as a preservative for various things, but not all aldehydes are used for that purpose. In fact, there are a number of aldehydes that are common in natural sources, okay, and they often have a pleasant aroma. Here is one particular aldehyde. It has this 6-membered ring with the double bonds. We'll talk about that in a little bit, but then it has a double bond to oxygen and a hydrogen attached on that carbon, and that is the aldehyde group. Okay, this particular one is benzaldehyde. All right, and a benzaldehyde is a component in almonds, and it actually contributes to the flavor and the smell of almonds, this benzaldehyde. Okay, another natural aldehyde also has this 6-membered ring with the double bonds, and this one, it has a few other types of functional groups. It has an OH, it has an oxygen with another carbon chain here. This would be an ether group. This is a hydroxy, or a hydroxyl rather, group. And then it also has, of course, the aldehyde group. Right? And this one is a compound called, by its common name, of vanillin. And vanillin, as the name suggests, is what gives vanilla its flavor. And artificial vanilla is largely this compound vanillin. Okay, and then one other one just to round out the examples from natural sources. Now, don't get the idea that all naturally occurring aldehydes have this six-membered ring on them, but these examples just happen to. And this particular one looks like this. Okay, it's quite often the case that you'll see a lot of double bonds in many biologically molecules of biological origin. That's not an uncommon characteristic. But here is our aldehyde group, a double bond to oxygen with a hydrogen on that carbon. And this one is cinnamaldehyde. Let's see, that would be, I think there's two N's there. Cinnamaldehyde. Okay. And as this name suggests, this is a component in cinnamon. All right. So just for interest's sake, these are some examples from natural sources. Aldehydes often occur, and they have this different aromas quite often. Formaldehyde has a rather unpleasant, kind of a pungent smell to it, but many aldehydes have a pleasant aroma. Okay, now related to the aldehyde, just in the same way that the ether is related to the alcohol, if I remove that hydrogen and put another carbon chain, if I take an aldehyde and I remove that hydrogen and I put another carbon chain, I'd have something that looks like this, right? I've got two carbon chains, and there's my double bonded oxygen atom. And this is called a ketone, right? Molecules that have this double bond to oxygen in them, and then where that carbon is connected to two other carbon atoms, that makes a ketone, right? And this group by itself, okay, where we have the double bond to oxygen, when we name it as a group, just like we say this is the methyl group or the hydroxyl group, and a hydroxyl group makes alcohols. So a carbonyl, right, a carbonyl group is referring to this double bond to oxygen. Anytime I have a carbon doubly bonded to oxygen, I'll call that a carbonyl carbon, or this is a carbonyl group, okay? So if I have a carbonyl carbon that is attached to two other carbons, that is a ketone. But if I have a carbonyl carbon, right, this is still a carbonyl carbon because it has a double bond to oxygen, but this carbonyl carbon is only attached to one carbon chain, and that makes it an aldehyde. Okay, and in this example here of formaldehyde, I don't even have any carbon chains, just that carbonyl carbon all by itself. Okay, so there's a lot of names that you need to be familiar with. Just whatever it takes, a lot of repetition is typically the best, I think. But just look at these and remember, a carbonyl carbon has that double bond to oxygen, and it makes a ketone when it is between two other carbon atoms. All right? It makes an aldehyde if it's just at the end of one chain. All right? So again, just in the same way that an ether is related to the alcohol, so the ketone is related to the aldehyde. Okay. Now let's look at another functional group, and this functional group also has a carbonyl carbon in it, but this time attached to that carbon is not another carbon chain, but an OH. Okay, it's kind of a carbon combination of a carbonyl carbon with a hydroxyl group. Okay, but all together, this is a carboxylic, the compound would be a carboxylic acid, and I call this the carboxyl group. Okay, so again, you see that YL, very common in the names of the groups. This would be the carboxyl group, and compounds that have the carboxyl group in them are what we call carboxylic acids. Okay, just as compounds that have the hydroxyl group are alcohols. Okay, so we have seen carboxylic acids, or at least one in particular, though we didn't recognize it as such. But you remember acetic acid from the acetate ion? Well, that's HC2H3O2. This is actually an organic acid. It's a carboxylic acid. And if we look at the formula for this, it has 2 carbons. It's a 2-carbon carboxylic acid. So here are my 2 carbons, and then one of them has the carbonyl and a hydroxyl group on the same carbon. And so this is what my acetic acid looks like. C2H3, there's 3 hydrogens there because I'm only showing 1 bond, and carbon has to have 4 bonds. And then I have 2, 3, 4 bonds to this carbon, so it can't have any more bonds. There's no hydrogens on that carbon. But I have C2H3O2, that's my acetate, and then here is the part that makes it an acid, right? You have to have a hydrogen. Now, organic acids look a little bit different than what we might expect, because usually we see that OH and we think, well, that would be a base. But in organic chemistry, this is actually an acid. That oxygen is tightly bonded to the rest of the molecule, and it doesn't come off. Okay, but this hydrogen, it will come off relatively easy, particularly when we have that double bond to oxygen, that carbonyl group right there on that same carbon that the hydroxyl group is on. It makes it where that hydrogen will come off very easily, and that's what I need for an acid, right? You remember the Bronsted-Lowry definition, a proton donor. So if this can donate that proton, if it can remove it easily, then that makes it an acid. There are 3 other hydrogens over here, but they are very difficult to remove. But because of those oxygen atoms there, it makes that hydrogen easy to remove, and therefore this is an acid, and that is the part that makes it an acid. It's still a weak acid. It's not anywhere near as strong as something like HCl, but relatively speaking, this hydrogen is easier to remove than those other ones in that molecule. Okay, so, and of course this is the active ingredient in vinegar. That's what gives it that vinegar flavor or smell. Okay, but there are other common compounds that have this acid group, this carboxyl group in them, And you have probably heard the term fatty acids. Well, any organic acid, this is what it is. It's a carboxyl, it has a carboxyl group, making it a carboxylic acid. That's an organic acid. So a fatty acid, actually much like what I've drawn here, if you ignore these other groups that I've drawn on there, this would look a lot like a fatty acid. Okay, a fat, this is a kind of a fatty chain because it's fat soluble. Okay, if you recall about polarity and solubility, compounds that are polar will dissolve other polar compounds, and compounds that are nonpolar will dissolve nonpolar compounds. Well, over here I have a polar group because I have these electronegative atoms, and but over here I have a long nonpolar part, and that nonpolar part is soluble in fats. Okay, so anyway, the fatty acids, you have that fatty part, and then the acid, that's where it gets its name. Okay, and once again, just as we saw with the ether and how it's related to the alcohol, an ether has that hydrogen replaced with a carbon chain, and just as the ketone is related to the aldehyde by the same way of removing that hydrogen and putting a second carbon chain there. So we have a similar case. If we remove this hydrogen of the carboxyl group and we put a carbon chain there, let's just throw in something here. Remember, you should be able to recognize these groups in any orientation. Okay, so if I showed something like this, and I had the hydrogen there, right, you should still be able to recognize, even though it's a different orientation, that I've got a carbonyl carbon with a hydroxyl group attached, so that is a carboxyl group, kind of from the carbonyl and hydroxyl carboxyl. You get that combination in the name. So be able to recognize it in any orientation, but just for this example, I'm going to draw it like this, and instead of a hydrogen, I'm going to put a carbon chain hanging off of that oxygen. So now I have that same carboxyl group, except instead of an OH here, I have another carbon chain. And this is known as an ester. Okay. Esters are quite common in organic chemistry. Many aromatic compounds are esters. In fact, they have a characteristic fruity aroma. There are many fruity type smells that are actually esters, and a few examples. One is if I have an ethyl group on my oxygen, okay, the oxygen that is part of my ester group, right? And then I have 4 carbons over here, and this is ethyl butanoate. Okay, that's the name. We'll talk about the naming of these different types of compounds a little bit later. We're only going to look briefly at naming of different types of functional groups just to kind of get a feel for it. But anyway, you recognize those same base names, the butan, for the 4 carbons in the chain, and then the ethyl group attached over there. And this particular compound is the major component of pineapple. Okay, and another one is the is methyl butanoate. So if I just, instead of having 2 carbons over here, I have just 1 carbon forming a methyl group, all right, but still having my 4 carbons on this side. So this is the pineapple, and this one is your ordinary apple. Okay, so just a single little CH3 group on there, and you get the difference between pineapple and apple. Both fruity flavors, but different in their own right. Okay. Okay. Another ester is the let's see here. This one I'm drawing a little bit differently, but looking the other direction, you should still be able to recognize this as an ester. All of these, even though they're in different orientations, you have a double bond to oxygen. That's your carbonyl carbon with the oxygen and a carbon chain. Double bond oxygen, oxygen with the carbon chain. The carbonyl carbon and the oxygen with a carbon chain. Okay, so it doesn't matter whether I put the oxygen on the right or on the left, or however it might be oriented. Just look for those characteristics, and that tells you that this is an ester. Okay, and this particular ester is attributable for the flavor of pears. Now, in natural substances like these, pineapple, the smell that gives pineapple its characteristic smell is not only this compound, but this is largely it's a major component. In any natural products, you always have mixtures, and every different compound will give it a slightly different characteristic in the smell. But this is the major component, and that's why the synthetic or the artificial flavors are never quite like the real thing. It's because they capitalize on the major component, but they don't have all the other minor components that the natural product does, that give it that really the rounded out flavor or smell. Okay, and some esters are they have a kind of a citrus type of aroma. One has this same 2 carbon chain on the one side, and but on the other side it has a long chain of 8 carbons, 2, 4, 6, 8 carbons there, and this particular one has the aroma of oranges. Okay. One last example that I'll give here, I've already drawn it, and is another compound that is in cinnamon. So just like I was saying before, these are one component among many in these natural flavors. Cinnamon, you have cinnamaldehyde. When you're smelling the smell of cinnamon, you smell not only cinnamaldehyde, but also this ester. And you'll notice there are similarities between these compounds. They both have that 6-membered ring with the 3 double bonds, okay, and then that's attached to a carbon with a double bond. All right, now remember, these rotate and they bend around all the time, so it doesn't matter that this one's drawn like that and this one's in a row. It's got that double bond there, and then the carbonyl carbon next. All right, the only difference is this part that I have circled there is in addition, in place of that hydrogen that's hanging off here. I have this ethyl group with the oxygen there, and that's what makes it an ester. But because of the similarities in these molecules, they also have a similar smell, and both of those work together to contribute to the smell of cinnamon, right? So in natural products, you always have a variety of compounds that contribute to the flavor. It's not just a single isolated compound, and that is often the reason why different artificial flavors don't really mimic the real thing so well, is because it's difficult to come up with all those different compounds to put into the flavoring. But you can isolate one or maybe two different compounds and get a pretty good replica of the flavor, enough to recognize at least. Another functional group that we'll look at is the amine. Okay, and amine, like ammonia, they come from the same root word, and amines have that characteristic nitrogen in them. Okay, that's what makes it an amine, is when it has nitrogen. And the nitrogen, it might have two hydrogen. You know, ammonia is NH3, so that would be your simplest amine, if you will. But organic amines have, it might have two hydrogens connected and with the nitrogen connected to a carbon chain, or you might have a different amine where you have two carbon chains attached and one hydrogen, or you might have an amine with three separate carbon chains all on there and no hydrogens on that nitrogen. Okay, and these three types of amines are given a designation to indicate what, whether it has two hydrogens, one hydrogen, or no hydrogens, or whether it has one carbon chain, two carbon chains, or three carbon chains. And this one, if it has one carbon chain, it's called a primary amine. Okay, a primary amine, and the primary is abbreviated with a 1 and then the degree symbol. Okay, if it has two carbon chains, we call that a secondary amine. Okay, and secondary is abbreviated with a 2 and a degree. So this would be a secondary amine. All right, and then here we have a tertiary amine, and the tertiary is abbreviated with a 3 and a degree. Okay, so primary, secondary, tertiary, depending on how many carbon atoms are connected to that nitrogen. One carbon in its chain, that's primary. Two carbons, there's one chain and then another chain, and then that hydrogen, that is a secondary amine. And then if I have three carbon chains, that is a tertiary amine. All right. Now, amines have a very characteristic property in that they often are present in molecules that have a very foul odor. Okay, even the simplest amine, ammonia, it doesn't really smell all that great. And there are many organic amines that are far worse than ammonia. For example, there is amine, it's actually a diamine. We have, if you have, let's see, a nitrogen here, and then 5 carbons, and then it's attached to another nitrogen. These are they're going to be primary amines. They are attached to only 1 carbon each. Right? Now this molecule is called cadaverine. All right, and there's a good reason for that. As the name implies, this is a compound that is present in cadavers and other decaying animal flesh. A very foul smell indeed. Okay, and then a similar amine to this one, having the only difference being there's only 4 carbons in between. This one is called by its common name of putrescine. Okay, and again, a very descriptive name from the putrefying flesh of dead animals. These compounds come from that material. It's actually the bacteria in the flesh. As it breaks it down, it produces these amines in the process, and that is what you're smelling. Other very bad smells, like the high school locker room type smells, those are going to be high in amine compounds. Okay, now just like compounds with the carboxyl group are called carboxylic acids. All right, the group with that that makes a molecule an amine, that group is actually called an amino group. Okay, so this is an amino group, and the molecule is an amine. All right, so just they're pretty much similar. This one is a little bit different in that it doesn't have the YL ending like many of the groups do, but it's an amino group, and then the molecules with an amino group are called amines. Now, amines are not all bad. You have surely heard of amino acids. Okay, well, guess what 2 functional groups are in amino acids? You've got the amino group and the acid group, or the carboxyl group. Right? So an amino acid, the simplest amino acid would be glycine, and it looks like this. There's the NH2 kind of looking backwards, and it is connected to a CH2, and then we have the carboxyl group. So we have the amino group, the carboxyl group, and that's why we call this an amino acid, because this is the carboxylic acid, and this is the amino acid. Yes, this is the amino acid glycine. It has 2 carbon atoms, and the amino group on 1 carbon atom, and then the other carbon has the carboxylic acid functional group. Okay, so a lot of the names of things that we are we hear about on a regular basis. It comes from the actual chemistry and oftentimes the functional groups of those molecules. Alright, now I am about out of space on this page, so I'm going to clear the page and let's kind of do a little recap. Okay, some of the functional groups that we have looked at. We have alcohols. All right, alcohols have that. We often abbreviate a carbon chain with the letter R. So we can write a general formula for alcohols would look like this. R, it actually stands for the word radical. That's what we call a carbon chain that is attached. Anyway, so this R just represents any type of carbon chain. Okay, so whatever carbon chain you have, an alcohol is one where that OH is attached. And we saw some examples, like isopropanol or 2-propanol, where the alcohol is on the second carbon. We also saw the case of like ethanol, right? This ethanol would look like that. And there are other many other types of alcohols. They all have that OH bonded to carbon. Okay, and you notice a difference between these three alcohols. And just like the amines, remember an amine has the nitrogen can be connected to 1, 2, or 3 different carbon atoms. Well, similarly, an alcohol, the carbon, if you look at the carbon that the alcohol group is attached to, and then you say, well, how many carbons is that carbon connected to? Well, if it's just on one, or if it's by itself, that is a primary alcohol. All right, so just like we had primary amines, we also have primary alcohols. All right, again, the abbreviation for primary being 1 and then the degree symbol. But if that carbon on which we have the hydroxyl group, if that carbon is connected to 2 other carbons, this is a secondary alcohol. Okay, a secondary alcohol has this alcohol carbon on 2 connected to 2 other carbons. Or you can think of it just, it's kind of in between like that, whereas this one is on the end. And then this one, you guessed it, that's the tertiary alcohol. Okay, tertiary is where that carbon is connected to 3 other carbons. All right, so the primary, secondary, and tertiary designations, they apply to alcohols as well as amines, but none of the other functional groups that we have looked at will utilize that designation. Okay, so we have alcohols, and then do you remember the related functional group to alcohols, where if I take that hydrogen and I replace it with a carbon chain, those are called ethers. That's right. All right, so an ether has a carbon chain and then oxygen, but instead of hydrogen we have another carbon chain, not necessarily the same one. The R can represent any carbon chain, whether the same or different. Okay, so an ether is related to the alcohol. right? So several of these come in pairs, right? The alcohol, the ether, and then we saw the aldehyde. You remember the aldehyde is where we had the carbon chain, and then it had a carbonyl carbon on it. But that carbonyl carbon was at the end of the chain, and it had a hydrogen hanging off of it. Okay, so that's an aldehyde. And what's the related one where I have an R group attached to that? I have a I have the carbonyl carbon there, but I have two R groups, two carbon chains. This is a ketone. Okay, so aldehydes are to ketones as alcohols are to ethers. All right, and then we have also a, and by the way, a very common ketone is acetone. Acetone has just two methyl groups attached to that carbonyl carbon. Right, that is acetone. Just a small, simple molecule, but very common and used as a solvent, as are many ketones. Okay, now we then had carboxylic acid. And the carboxylic acid has the carbonyl carbon again, but it's a carboxyl. The carboxyl group has the carbonyl and the hydroxyl together. There's my carbonyl, and here's the hydroxyl group. Okay, so that is my carboxyl group. You should be familiar with both the group name as well as the compound name that has that group in there. So a carboxyl group is the one that makes a carboxylic acid. Okay, and here, this for the alcohol, this would be the hydroxyl group. Okay, and as an aldehyde is to a ketone, a carboxylic acid is to a compound that looks like this, where I replace that hydrogen with another carbon chain, and that is an ester. Okay, so once again, these are related compounds. Often, several of these come in pairs where you've got an H, and then you replace that with an R. An H, you replace it with a carbon chain R group. Okay, an H, you replace it with an R group. So that will help you in memorizing these. Memorize them in pairs: alcohols and ethers, aldehydes and ketones, carboxyl, the carboxyl group, and carboxylic acids and esters. Memorize them in pairs. Okay, and then we looked at amines, which have the nitrogen in them. Okay, they look something like this: R3N, where I have three different carbon chains, and in this case, R may also be hydrogen. Okay, or I could write it like if I wanted to distinguish between the let's see here, This would be an NH, and I'd have NH2. This is a primary amine, a secondary amine, and this would be a tertiary amine if my R group represents some kind of a carbon chain and not allowing just hydrogen. Okay, so 3 different types of amines: primary, secondary, tertiary, just like we have with the alcohols, looking at how many carbon groups are attached to that nitrogen. 2 carbon groups, secondary. Only 1, it's primary. If 3 carbon groups, then it's a tertiary amine. Okay, but the group name is an amino group. All right, and all right, so let's look at a couple of other functional groups that are common, or at least that you should be able to recognize. They're less common, but depending on what you will be pursuing, you may see these in other classes. Okay, so these are the main ones, but then there's also the thiol. Okay, a thiol has sulfur in it. Okay, so it would look like R and then SH. Okay, so this group is known as the sulfhydryl. Okay, sulf obviously for the sulfur, and the hydryl for the hydrogen, kind of sulfhydra, and then the YL ending because we're naming that as a group. This is known as the sulfhydryl group, and the molecule is a thiol. That's the class of molecules. Okay, and these compound. Well, first of all, the thiol is this word comes from the Greek word thion, which means sulfur. Okay, so thion is sulfur in Greek, and if you combine that with alcohol, okay, because this is kind of like sulfur and oxygen are both in the same family of elements, the same group, and so this is very similar in many respects to an alcohol. And so you take that sulfur, combine it with alcohol, and you get thiol. All right, so that's where the name comes from, kind of combining the sulfur with the alcohol, since this is like an alcohol. Okay, now these compounds are often very smelly. Okay, in usually not the most pleasant smells, different than the amines. These are not very nice smelling substances either, but these have that characteristic sulfury smell, but not necessarily a bad smell. There are pleasant sulfury smells. You are familiar with garlic. Well, garlic has that sulfur or that thiol, those thiol compounds in it. But most thiols are not the most pleasant smelling substances. For example, natural gas is actually an odorless gas, but it is scented with a thiol. Okay, it's the thiol that we smell when we smell a gas leak. It's added to the gas so that you can detect its presence in a leak, and it's not generally considered a very pleasant smell. and also thiols are in the gases that escape when you have flatulence. Okay, so generally not the most pleasant smells, but different than the amine compounds. Another property of thiols is that they are very much attracted to mercury. And in fact, for that reason, they're often referred to as mercaptans. Right? The term mercaptan comes from a combination of the Latin words mercurium for mercury, and then captan for capturing. So this in Latin means capturing mercury, and in fact I used to work for a company that produced a compound that had this mercaptan functional group on it, and we used it for that very purpose, to collect all the mercury out from water supplies. It was based on the mercury capturing properties of that thiol group. Okay, so these are some different functional groups that you should at least be able to recognize, and in a few cases, like the amines, identify whether it's primary, secondary, or tertiary, as well as the alcohols, and note the pairs to aid in memorization of these functional groups. Particularly if you are pursuing any kind of biological career, whether nursing or anything else. In your other biology classes, you're going to see some of these functional groups again, and so this would give you a bit of a primer for that. All right. One other common functional group, which we're very familiar with from inorganic chemistry, is the phosphate group. Okay, we know phosphate is PO4 with a -3 charge, right? Well, this can also join in with organic compounds. You've heard of ATP, perhaps. ATP, adenosine triphosphate. Well, it has 3 phosphate ions kind of all connected together. And what it looks like is, you would have your R group, and then the phosphate. There's your oxygen, and then you have phosphorus. It has 4 oxygens, looking something like this. And if you were to draw the complete Lewis structure, you would find that there's a double bond to one of those, and it's only the other 3 that form the charges. Okay, but in organic phosphates, typically you'll have a hydrogen on here, but you could have some other group as well. But essentially the same thing as the inorganic phosphate. You have that PO4, but it's connected to a carbon chain in the functional group. Okay, so this is a summary of the different functional groups that you should be familiar with in this class. Alcohols, ethers, and then be also familiar with not only the different types of alcohols, primary, secondary, or tertiary. Also know the name of the group itself. When you name it as a group, that's the hydroxyl group. But the compound that it forms is an alcohol. All right. And then aldehydes have that carbonyl carbon. That's another term you should know. The carbon that has a double bond to oxygen is a carbonyl carbon. Again, the YL often used to name the groups. As a group, it ends in the YL. Okay. Ketones have that same carbonyl carbon, but they have two R groups. And then you have the carboxylic acid. There's the carboxyl group, and you have esters as well. Similarly, they just have an R replacing that hydrogen. Then the amines have the nitrogen. Thiols have that, they're like the sulfur alcohol, as the name implies. Just like the carboxylic acid, you have the carbonyl and hydroxyl group. Both of those combined together, carbonyl and the hydroxyl, in one functional group. Okay? And one other term you should be familiar with, if you have something like this. Here's a carbon chain, and let's say you have a side group that is nothing really functional about it, but this group you would name as ethyl, right? Because it has two carbons, and then you change it to that YL ending because it's a group. Well, in general, any kind of a group that is just a standard alkane, or maybe an alkene or kyne, which aren't all that much more functional. They're pretty similar to the alkanes. In general, we call these alkyl groups. Okay, so an alkyl, like alkane, alkene, alkyne, an alkyl group is just any group that is just a hydrocarbon and no other real functionality. Okay. There are also, we've seen a few examples where you have a six-membered ring, and when that ring has those three double bonds, we call this an aromatic compound. Okay. Or an aromatic group. Okay, so the reason those types of compounds are called aromatic is because they are often aromatic. They have aromas associated with them. An example is this compound, which actually has two rings that are fused together. They share a common, let me do this right here. There's a double bond there, there, and there. All right, and then here and there. Okay, so the same sort of thing. You've got the three double bonds for each of those. This compound is known as naphthalene, or by its common name, mothballs. All right, so if you're familiar with mothballs, you know that they have a very definite aroma, and that's why these rings, six-membered rings with those three double bonds, have been called aromatic, because they're often in compounds that have an aroma. Okay, so just be able to recognize those. You can see the aromatic groups, and then an alkyl group, an amino group would be one where you've got your R chain, and then there is an amino group. Okay, so, and this would be an amine, the compound. All right. So be familiar with all of these terms, memorize them, and be able to associate them with the functional group that they represent.